Hello, hello, hello. Mm, okay, I'm back. Yesterday's cut off was because of video bitrate. Okay, I set it up. I said it was around 8,000, 9,000, and it was too much for my internet to handle. So for 13 days, it was good, right? No one was using it, but yesterday it was more traffic, I guess. Everyone was using it, so I had to decrease the bitrate, and everything is fine. Yesterday's I had some work to do, and we were at Bayes theorem. I finished Bayes theorem, and then I didn't do distributions. Okay, normal distribution, Poisson distribution, binary distribution, binomial distribution. I didn't do any of it. Okay, so why am I nervous? Hmm, it's just so random, but I'm nervous today. Why I don't know. Is it because of you guys? Well, who cares? Okay, fine, fine. It is fine. Um, yeah, never mind. I wanted to finish this yesterday, right? But I'm not gonna say any flag shit, okay? Because I have to do this today, and I don't want to say anything other than that. If I say that, it will not be finished, and we have enough time. Let's get started. We were at this yesterday, right? We were at solved examples. I was looking at this, I guess. Then we were looking at this. We'll be looking through example 3, 4, 5, and some practice questions. These are for me. I have not done this one too, conditional probability one, but when I get time, I'll do it. I didn't get time. Nowadays, time is so valuable, guys. And this 2 hour is also so consuming. Oh, I was talking about, right. I wanted to do this, right. I was also thinking about integrating. Yes, this is not written by me. This is written by AI, obviously. If I have AI, I will use it, man. This is for mm, this is for how I want to integrate a model in my chess, right? And there are some flaws, I know, but basically I'll be doing a separate Python project. Okay, this was my idea. I told the AI to make some setup, but don't know what it did. This is not actually working, right? So I thought this would work, either this or this, inference for API, and so I have to make engine integration layer for the AI to the model to interact with my code. As in my code, I have brilliantly, I'll say brilliantly, uh, done this, right? And this is not efficient for a board. for board representation. Like, this is not efficient, this is just generic. If you think about it, you can do it like this, and this is that. Okay, so I looked into it. There were bit boards, fin, uh, pgn, and different types of notation that I could use, or I could have just made bit boards for that to calculate, right? That's why I had a hard time figuring out how to calculate the positions, or how to restrict the pieces to be moved, right? So what it's recommending is that exporting the model to ONNX to load to C++. It can be harder to set up, so I'll be doing that through Fast API. Fast API. I'll be doing through Fast API. If I can, then I'll do through this. My initial thought is I want to integrate Stockfish in this first, using that engine integration layer, right? And I'll figure it out if it works in this. After it's working in this, I'll build a separate project for my model, right? And that will make my timeline easy, right? I can't be doing this work and this work too, right? So I'm differentiating the things. First of all, I'll complete the build up of this whole. Okay, I'll completely build it with integration with Stockfish, as it supports Fin. I'm thinking of converting uh, this to Fin notation to pass it to the engine, and the engine will give me Fin notation again, and that Fin notation will be displayed in the board, right? Uh, as a Fin notation is for one snapshot of a sequence. So that is my initial thought, and it can change, but this was actually what I thought for yesterday's night session. I don't have enough time, so I have to do this at night, and I was so sleepy. Um, and this is just the fillers that it uh, I just said it to analyze the code for me to for it to be familiar with my situation, right? So that's why I tried giving it that prompt, and it uh, generally gave a uh, code based code based explanation, right? So it was trying to explain to me what database chess engine is, but it is just basically two types: one traditional way, one neural network way. We can do it two ways, but I want to learn AIML, right? So I can't be doing traditional way, but we can integrate that too. I was also thinking about that, but we can make a wrapper or something. I talked about making a wrapper, but that will be further down the line. More than this, I will be doing. First, I'll be doing. Wait, okay. This is the next project. It talked about. This is just it making some. I'll be doing supervised learning first to predict the moves, right? And when it gives fin notation, it sends the optimum move that can play. Okay, I want to make it so that the model plays around my level, right? So I'm around 1100, but if the model plays, I want the model to play around 1500. Okay, that will be the initial goal, and don't know if it would work. 500 is maximum. I have my expectation at 500. I have my goal at 1500. Don't know where it will go. I looked into some other guys making it. They made in trained in 3070 GPU with enough data set with good architecture, and it was around 1700, right? So that's why I made my goal to 1500, and I thought it would be possible. And this laptop is not good, and I'm in laptop, right? So I can't be training in this. So I'll be using Google Colab. That will also be a problem if it doesn't work out. These are just the filler codes, but it is trying to do. I don't know. It's just trying to recommend me the starting point where I should start. But I will figure it out when I start. More than that, I have to complete this project first, project one first. Then I will move to that ML, that model. Okay, so it's recommending me free options and paid options. By the way, the integrated AI in VS Code, if you use Claude, it's too good. It's too good. When you give it a prompt to write in something, then it writes so easily, and it is just so easy to interact with it in the VS rather than in the wave site. Okay, so I prefer this than others. And I thought about it, but we could also write it in latex, right? So latex, it can also write in latex, so that will be helpful. I'll think about it. And Google Colab training script, I don't know what it's trying to say, but I will look at it later when the time comes. And I wanted to know how the model will interact with the code, right? So it's giving me two options, from API and from ONNX export. Export. Okay. So my friend recommended this, to use this, but I don't know, and we'll figure it out eventually. Or first we'll do that stockfish one. I'll check how it will go, and if it is good, then we'll do it that way. Also, it's for development and it's for distribution. And yeah, this is the game integration part, right? It wants to add fin generation to board class. Okay, and I have to do it, but the files are cluttered. Okay, this is not the way to manage the files, right? So I have to do that too. So this API communication is just there. I'll take that reference if I want, and I have to integrate it to so pen notation is like this. If you don't know about it, it's so efficient, and it will take a one snapshot of a board, right? And it is saying to me, I don't know what about Python, but the model will be model, right? It will not be Python. So why is this doing like this? I don't know, but it is giving me this as the a response from the model, right? And I don't think this will be good enough. I have to look into what the software does to integrate to my, then I will be thinking about what the response will be from the model. So it's like this, and it's recommending me the setup step by step implementation, right? This is not good, and I have to revise it. It's not really great, and it's giving me data set 2, but I already found some good one. It's elite, right? Here it is. I'll be looking at this. These are good as it's 2000 per plus elo game. So king base also can be done, but don't know about that. And I have to look if I can hook it up to Google Colab, right? I don't have much space in my drive too. Uh, in Kaggle, if it can be done in Kaggle, then it is also good. And file structure summary. So this is just don't know it's hallucinating or not, but it was just part of my prompt, I guess. And learning path. Okay. I gave it the prompt slash saying that I am trying to learn AI ML in the path also. So as in engine can be of two types. So I wanted to give it a specification about what I am trying to do in this project, right? So this is about that. And yeah, don't know what this is, but key points. Yeah, these are key points from training cloud. That's correct. Start simple. That is also correct. And API communication. I don't think I can build that neural network one. It's too advanced, and I'll be going through deep learning after ML. So supervised learning it is. And okay, one thing I have learned is from doing projects, you will learn a lot. So don't try to sabotage your own project by letting the AI do it. Okay. Uh, if you do your projects by your own, or if you try and do stuff like this brain rot type stuff, adding course in unwanted part, commenting out good parts that you don't want to leave because you have written it. I i have done this. I have not uncommented it, or I have not deleted it. Sorry, I have not deleted it because I thought it would work, and like it was brainstorming. This was just in my heart, so I didn't do that. There are a lot of things that are commented out here. This one, okay, and this also works. Is what I figured it out. Okay, and this one was after some time. Okay, this one just this one was just recommended by AI. Okay, you can do this efficiently like this, but this one I figured it out. Okay, um so there is some love in it. And if you this is just HPP file, right? And these are just function definition declaration call, right? So these are just, I don't know what I was thinking, but looking at this, I can see that I have made it, right? I have done this much work, and it is not efficient, and it is not what others thinks that it's efficient, right? But I learned from this. So this project is for me to learn. If you What I wanted to say is, after you make a mistake, then you will know that it's a mistake, right? And then you will do the right stuff. So the process of figuring out from having yourself be wronged and then doing something right gives you that wisdom of not doing that wrong thing again, right? So you will learn a lot while doing a project, short and sweet. And we'll be looking at this, already completed it, but looking at some examples. Then, okay, already a lot of time, half an hour already gone. So let's start. A card from a pack of 52 cards is lost from the remaining card of the pack. Two cards are drawn and are found to be both hearts. Okay, find the probability of the lost card being a heart. We are letting e1, e2, e3, and e4 be the events of losing a card of heart, clubs, spades, and diamonds respectively. Okay, heart, club, spade, and diamonds. Then P1, probability of losing a card of hearts, probability of losing a card of everything is 13 by 24. Oh, okay. Uh, then let probability of probability of losing a look, probability of drawing two hearts from the remaining 51 cards be given that losing a heart of card, it will be a combination of 2 is to 12, right? And it will be 12 into 11 divided by 2 factorial. This is the factorial. I can do that in calculator. We'll just let it be like this, and this is the heart of missing. Okay, and probability of drawing two clubs given that a card of club is missing, right? Card of club is missing, 51 2, one card is missed, so that is why 51, and it's figuring out for two cards. So this probability of drawing two spades given that the card of heart is missing, two cards 51, two cards 13. So this is the probability and probability of two diamonds, right? So therefore the probability of lost card is being a heart given the two heart are drawn from the remaining 51 cards is uh, multiplication and division of e1, multiplication of probability e2 to e when given e2, then this is the division in e1. No, if it is being divided pe1, then this and this should be cut. It will only be this remaining. Hmm? Mm-hmm. Correct probability is 0.22. Okay, 1 by 4. Let us look. 1 by 4 is the probability of e1, right? Probability of e1, and like this is type mistake again. No. Oh, this. Yeah. It's divide. It's divided with e1 with a. So this as a whole is one statement for what's it called? I forgot. Mm. Hmm. What is this bizarre? These two will just be caught and it will be one, right? Yeah, one. It will be one. Yeah, it will be one. Why am I figuring out that? Suppose 15 men out of 300 men and 25 women out of 1000 are good orators, right? And orator is chosen at random. Find the probability that a male person is selected. So 15 out of 30 men, total men 300, sorry, 300. It was not 30, it was 300, right? And 25 out of 1000 women, good orators are 15 men, 25 women, total number of good orators 15 plus 25, 40. And the probability of selecting a male actor is number of male orators, not actor, orator. Orator, total number of orators, it's 3 plus 8. Orator is someone who talks about, right? Public speaker, right? Talks. Eloquent, skilled, official speaking, which I don't know. Uh, I can't really communicate exactly what I want without stopping myself in the middle, thinking about the words that I want to talk about. A man is known to speak the lies 1 out of 4 times. He throws a die and reports that it is 6. Find the probability that it is actually a 6. Okay, there's speaker who lies. In a throw of a die, let event of getting a 6, event of not getting a 6, and event that the man reports that it is a 6. Okay, there are 3 events, and event 1 probability is 1 by 6, as event of getting 6 is 1 by 6, and event of not getting 6 is 1 minus 1 by 6, which is 5 by 6, and the probability that the man reports that 6 occurs when 6 has already occurred. Okay, that 6 occurs when the 6 has already occurred is the probability that the man speaks truth, right? So it's 3 upon 4, 3 by 4 times. E is to 1 is reports to is going to speak a lie 1 out of 4 times. 4, 2, 3 is to 4. 4 to 3 is to 4. Is that right? 1 by 4 into 1 by 6. Hmm. 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 Uh, 0.75, right? 0.75615, and the probability that probability that the man speaks the truth, how is calculated? It's calculated into E. Um, E of E1 will be E of E is event that the man reports that it is a 6 when speak lies out 1 out of 4 times. 1 out of 4 times that should be taken out, right? Getting a 6 even that the man report it to be 6 by base 0. 3 is to 4. 6 and this 3 slash 8. Okay. Uh, I didn't really get this. Why did I overlook it yesterday? Don't know. Let me look at it here. Die and records it. So, required probability is step by step. Die is so 6. Not so 6. My request that 6 occurs on the die. Right? 1 by 6, 5 by 6. Now, these two E1 is 3 by 4. Is it? Oh, it's 1 by 4. Oh, got it. Am I so dumb, bro? If your probability of getting the man reported is 1 by 4, 1 out of 4 times, it's this, then obviously this is 3 out of 4 times, right? Or am I wrong? No, I'm right. I'm right. Then you will find out Bayes theorem, and Bayes theorem is that given 3 by 8 is the answer. 3 by 8 is the answer. Okay, got it. I thought this was also calculated and figured out, but this should be done first, and then 1 minus 3 by 4. 1 minus 1 by 4 will be 3 by 4. Okay. Normal distribution. Uh, okay, the normal distribution, also called the Gaussian or Bell-shaped distribution, is one of the most commonly used probability distributions in statistics. Gaussian Bell. Yes, IAN or Bell-shaped distribution. Yes, is probability distribution in statistics. It is symmetric around the mean and forms the characteristic bell-shaped curve. Right, bell-shaped curve. It plays an essential role in statistics, especially in central limit theorem (CLT). In central limit theorem, most valuable cluster near the mean and probability decreases. Most values valuables. Most values cluster near the mean and the probability decreases as we move away from it. So it makes a bell-shaped curve like this, and near the mean the values away from it, right? Then it can be observed in above image that the distribution is symmetric about its center, which is mean. 0 is this case. Can we observe that the above image that the distribution is symmetric, center which is the mean, is symmetric either way. This makes the probability of events at equal derivation from the mean equally probable. The density is highly centered around the mean, which translate to lower probabilities for values away from the mean. Probability density function PDF. It has come to this. Uh, okay. Probability distribution. Probability density function (PDF). The probability density function of the normal distribution gives the likelihood of a continuous random variable taking a specific value. The formula is 1 by sigma root under square root of 2 2 pi e to the power minus 1 by 2, where there is x minus mu by sigma whole square. So it's probability density function of normal distribution that gives the likelihood of a continuous random variable taking a specific value. Okay, where mu is mean center of distribution, sigma is standard deviation spread, and x is the value for which we calculate the probability. To simplify this formula, we use the Z score, which tells us how many standard deviation value is from the mean. Z score is equals to x minus mu by sigma. A larger Z score means that the value is farther from the mean, giving a smaller probability due to negative exponent. Values near mean have higher probabilities. This behavior follows the 68 95 99.7 rule. 68% of the value lie within one standard deviation from the mean, 68 within one standard deviation, 95 within two standard deviation, and 9.7 within three standard deviation. Expectation. Okay. Mm, The expected value Ex is minus infinity to infinity x fx x dx. For the normal distribution, the formula becomes E of x 1 by sigma under 2 pi minus infinity to infinity x e power minus 1 by 2 x minus mu e power 2 dx. For the normal distribution, the formula becomes ex. This one is same as PDF density function. The expectation and expected value Ex of random gives up a measure of the center of distribution for a normal distributed random variable x with parameters mu and sigma square variance. The expectation is calculated by integrating the product of random variable and its probability density function. Why am I saying destination? It's always density function over all possible values. So minus x mm, minus infinity to infinity x fx x dx. Integration of x fx over minus infinite to infinity. For normal distribution, the formula becomes this, where x in front for this is the function, right? Fx is 1 by sigma root under 2x and e to the power minus 1 by 2 x minus mu and sigma square. So that will be right here, this, right, and this part is constant, which is thrown outside integration. We can simply simplify this by breaking into two parts. The first part involves integrating x mu, which is symmetric about the mean, and its result is 0 because the distribution is symmetric. The second part involves multiplying the mean by total probability, which equals 1 since the area under the normal curve is always 1. Okay, the second part involves multiplying the mean by total probability, which equals 1 since the area under the normal curve is always 1. So area under the normal curve is always 1. Thus we find expectation is equals to mu. This tells us that the expected value of a normal distribution is simply the mean, variance and standard deviation. Variance and standard deviation. The variance of a normal distribution is the square of the standard deviation, denoted as sigma square. It measures how spread out the values of the distributions are from the mean. Standard deviation, sigma, is simply the square root of the variance, right? Standard normal distribution. In general normal distribution, if the mean is set 0, if the mean is set to 0 and the standard deviation is set to 1, then resulting distribution is called standard normal distribution. Mean is 0 and the standard deviation is 1. The formula for probability density function of the standard normal distribution is fx, given 1 root under 2x e to the power minus x square by 2, where mu is equals to 0 and sigma is equals to 1. Symmetric around mean, and its PDF defines the shape of the bell curve. Cumulative distribution function, CDF. This one is super important, and the cumulative distribution function, CDF, is the normal distribution of the normal distribution does not have a closed form expression. As a result, pre-computed values from standard normal tables are used to find cumulative probabilities. These tables specifically provide cumulative probabilities for the standard normal distributions. Uh, I'll come back. Okay. Yep, I'm back. I just got up to get something to eat. I can't stop without eating. Let me try. Uh, I'm getting hang up with. Okay, I'm getting excited to read. That's a new thing. For the best of wishing. Oh, yeah. Oh,
Grips on your ways, front way, back way. You know that I don't play. Streets not safe, but I never run away, even when I'm away. OT, OT, there's never much love when we go OT. I pray to make it back in one piece. I pray, I pray. That's why I need a oneness. Got a Hennessy in my hand. One more time before I go. Higher powers taking a hold on me. I need a oneness. Got a Hennessy in my hand. One more time before I go. Higher powers taking a hold on me.
Baby, I like your style.
Strength and guidance, all that I'm wishing for my friends. Nobody makes it from my ends. I had to bust up the silence. You know you gotta stick by me. Soon as you see the text, reply me.
bro, why did I see N as a R?
We got no time, and that's why I need a oneness. Got a Hennessy in my hand. One more time before I go. Higher powers taking a hold on me. I need a oneness. Got a Hennessy in my hand. One more time before I go. Higher powers taking a hold on me.
Bro,
I need a oneness. Got a Hennessy in my hand. One more time before I go. Higher powers taking a hold on me. I need a oneness. Got a Hennessy in my hand. One more time before I go. Higher powers taking a hold on me.
what am I doing?
Girl, I got you so high, and I know you like. So come on, push it on me. If it feels alright, wanna drop it low and bring me up. No, she doesn't mind.
Bro, I just set it up. I didn't start. I didn't notice that. What became of my mind? Sequence. Oh yeah. Done. I fumbled here. I fumbled here. Here. Sorry. I fumbled here in the. But what's it? So much.
कभी कभी आदती जिंदगी में यूं ही कोई अपना लगता है कभी कभी आदती वो बिछड़ जाए तो एक सपना लगता है ऐसे में कोई कैसे अपने आंसू को बहने से रोके और कैसे कोई सोच दे everything's gonna be okay कभी कभी तो लगे जिंदगी में रही ना खुशी और ना मजा कभी कभी तो लगे हर दिन मुश्किल और हर पल एक सजा ऐसे में कोई कैसे मुस्कुराए कैसे हंसते रहते खुश होके और कैसे कोई सोच दे everything gonna be okay सोच जरा कर जा तुझको हम कितना चाहते हैं रोते हैं हम भी अगर तेरी आंखों में आंसू आते हैं गाना तो आता नहीं है मगर फिर भी हम गाते हैं याती मान कभी कभी सारे कहाँ में अंधेरा होता है लेकिन रात के बाद ही तो सवेरा होता है कभी कभी अगली जिंदगी में यूं ही कोई अपना लगता है कभी कभी आदती वो बिछड़ जाए तो एक जमना लगता है आदती हंसते 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 जो जरा नहीं तो बस थोड़ा 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 मुस्कुरा
Shoot, shoot. That's good run. I did it. This was it. And then this is good.
तू खुश है तो लगे कि जहाँ में छाई है खुशी सूरज निकले
There are so much copyright, but I don't care. There's no water. Buttu, 1, 2, 3. Okay, let's look through distributions. I don't know what my eyes were seeing, but because of this light, the sunlight is affecting my eye view. That's why I'm not able to read something correctly. Okay, screen is shit. Even though you are looking at good screen, but mine one's shit to look at. So, cumulative distribution function (CDF). The cumulative distribution function (CDF) of the normal distribution does not have a closed form expression. As a result, pre-computed values from standard normal tables are used to find cumulative probabilities. Okay. These tables specifically provide cumulative probabilities for the standard normal distribution, right? It gives probabilities for standard normal distribution. For a general normal distribution, the first step is to standardize the distribution by converting it into a z-score. Once standardized, the cumulative probability is calculated using the standard normal distribution table. Right. This process has two key benefits. One, only one table is needed to calculate probabilities for all normal distributions, regardless of the specific mean and standard deviation. The table size is manageable, containing 40 to 50 rows and 10 columns. Right. This one is given in my exam to take. This is constant with 68 to 95 to 99.7 rule, which is this one. 68% of in one standard deviation, 65 and 95 and 99.7 of values lies within 3 or less than plus minus 3 standard deviation of the mean. Therefore, probabilities beyond x is equals to mu plus 3 sigma become extremely small and are treated as approximately zero. Okay, the values outside this box are treated as zero, as it is too small to to exactly write that on not in this table, I guess. 0.99, 1.92, right? Yeah, like that. Example finding probabilities problem. Suppose that current measurements in a strip of wire are assumed to follow a normal distribution with a mean of 10 milliamperes and a variance of 4 milliamperes. What is the probability that a measurement exceeds 13 milliamperes? Okay, let X denote the current in milliamperes when we are tasked with finding P. Probability of X is greater than 13. Standardize X by converting it to a Z score, Z minus mu by sigma, which is 1.5. Now X greater than 13 becomes equivalent to probability of Z is greater than 1.5 in the standard normal distribution. From the standard normal table, find the value of Z, probability of Z, which is less than 1.5, here 1.5 and 5, 1.5, 0.9339, right? This one. And so, TZ greater than is given through this, which which is this. We want this, and it's 0.06681. Thus, the probability that the current exceeds 30 milliamperes is approximately this much, meaning 6.7%. uh, Probability implementation of normal distribution in Python. We here we use numpy, matplotlib, cburn libraries for implementation. I don't think it will give me the output, as there are yeah, it will show error, right? Can't import. Normal distribution of random data. Cborn, matplotlib, numpy. Applications of normal distribution. The normal distribution is incredibly versatile and is used across a variety of fields: scientific research, measurement errors are normally distributed, helps in making this distribution important in experimental design and hypothesis testing. Finance in stock market analysis, returns of stock prices follow a normal distribution. This helps in risk assessment and portfolio optimization. Engineering manufacturing processes such as dimensions of parts produced can be modeled using normal distribution. Psychometrics, test scores, IQ scores are assumed. Healthcare, biological measurements, mastering the standard normal distribution helps in deeper understanding of probability, which enables more accurate data interpretation and decision making. Mm, this one is true. This one. Zero and one. continuous random variables taking a specific value. Formalize this. Okay. Now binomial distribution in data science. Binomial distribution is used to calculate the probability of a specific number of successes in a fixed number of independent trials, where each trial results in one or two outcomes, success or failure. Mm, mm, Let me search for one thing. 93 ambitious. Mm, okay, upload speed is 78. Mm, yes, my stream is good. This is enough bitrate, I guess. Yeah, this is my question. Huh? Oh, just four of these. Damn, this looks phenomenal. Damn. Damn. Oh, damn. They own more storage than literally anyone. Google had quietly been the top buyer of hard drives for a while and just might have been partially responsible for a global shortage or one or two. Damn. For a one. Back when I worked there, Google was technically the world's single largest manufacturer of computers if you counted the ones they built for their own data centers. Their data centers are confusingly large, like bigger than some towns, like kind of large and packed tight. They get the hardware for extremely low prices, below even a normal zero margin rate, and very high volume, and often build their own components. IIRC, they don't know what IIRC, they designed and built their own SSDs, for example. And did I mention tape backups? Yeah, they have tape backups of everything. So if your data lasts more than a week or two, there will also be periodic copies across multiple backup tapes. Which reminds me of another reason for the encryption and another complication for the deduplication. Any data you indicate you want to delete has to be completely purged from everywhere within a given time frame of when you click the delete button. Oh yeah, including from the tape backups. The policy is called wipeout and it applies to everything enforced by the privacy team across all products. So they keep a grace period so you can undelete for a few weeks in an emergency. It's several weeks before full wipeout takes effect. But deleting files from tapes is not feasible, so every file is actually encrypted using unique per file key, and that unique key is what gets encrypted with your account key. The unique key does not get stored on tape. Then if you delete the file, they delete from tape by deleting all copies of the encryption key, making the file on tape permanently unreadable. Oh, damn, interesting. Never mind. Bro, they're so badass. This video is also being stored in YouTube platform, right? It can be accessed through YouTube. So, oh, this video too. It suddenly came to my mind how they store such a big amount of data, right?
You can't really talk about storage at Google without talking about how our production systems work. How are all the hard disks and flash drives on individual machines connected? Let's boil it down. Data is stored in hard disk drives or solid state drives. SSDs and HDDs are deployed separately from the applications. For example, they can be stored in a dedicated storage tray like this one. In other words, we separate storage from compute. Data needed by a machine is typically not even in the same rack because machines can access data in a different physical location through our robust global fiber network. Splitting storage and compute lets us scale them independently as demand grows, and Machines can process requests much more efficiently. We organize storage and compute racks into rows of physical enclosures, organizing groups of enclosures into clusters, and putting multiple clusters in a single data center. Each cluster depends on their own power, cooling, and network infrastructure, a deliberate part of how we design for data protection and reliability at scale. We've built our own warehouse-scale machine out of hundreds of thousands of relatively inexpensive machines. At Google, it's rare to dedicate an entire storage appliance in our data center for storing only one product or service's data. Instead, we spread a workload's data across multiple machines, and workloads share network access to that storage. Encryption is inherent in our storage systems, and all data is encrypted prior to being written to disk. But how does Google make storage accessible and scalable across a global fleet of machines? Remember, at planetary scale, it's not unusual for individual machines, racks, or even entire buildings to periodically fail. So we need to build software to make the data stored on them durable. That way, when they fail, no data is lost. Every layer of our storage stack, down to the file system and the layer that writes to storage devices, is a shared service. Services like search, photos, and Gmail workloads share machines at the data centers. Resources within each machine, like compute and memory, are allocated to each service. At a machine level, disk, or D for short, is a system that exposes the hard disk and SSD drives attached to individual machines to other services in the cluster. It manages access to each machine's disk capacity to maximize utilization. At the cluster level, most data we store has high durability and latency requirements, so we built a file system called Colossus on top of D, which is a foundation for many services like cloud storage and Bigtable. At the Colossus level, files are broken down into a set of chunks that can be stored on different machines in the cluster. This data replication across machines is the key to fast recovery and fault tolerance against things like network failures. For a given chunk, Colossus identifies a machine to write the chunk to, and the client sends the chunk to the D service that runs on the target machine to perform the write. Security is ensured through the encryption of each chunk, and each chunk has a unique encryption key. Because a single machine can be running multiple services, and conversely, a service can be running on many machines, services are constantly adapting to the amount of resources they use. Now you can see how distributed data better utilizes our machine capacity and gives Google Cloud Services higher reliability and performance. For Google Cloud users, you have the option to store data on local solid-state drives, zonal persistent disks that map to clusters across zones in the same region, or regional persistent disks across cloud regions or even storage buckets. You can store data in a single region for high performance, dual region for high performance and high availability, and multiple regions for the highest availability. Your data maps to different clusters and protects it from zonal and regional failures. D and Colossus manage access to the storage, store data safely and securely, and efficiently use our hardware so you get the best performance possible. All of this is possible because of the speed of our network fabric. More on that next time on Discovering Data Centers.
Let me check something.
Welcome back to my podcast. Thank you so much. Means a lot. आपको क्या लगता है मैं इंट्रोवर्ट हूँ या एक्सट्रोवर्ट?
मुझे लगता है आप pervert हो. Can someone help me, please?
Tell me something that blows your mind.
The fact that my chest is the back of my back, but my back is not the chest of my chest.
I'm getting chest bumps.
I'm scared.
जिंदगी में सबसे ज़्यादा डर किससे लगता है?
Expectations. My father. My father's expectations.
Expected goosebumps.
Are you stupid?
अपनी माँ के बारे में चंद शब्द.
माँ के बारे में I think माँ, she's the wife of my father.
So unique.
Is it worth it? Is it worth it? Damn. Last seen on 2024, active now. Third year. Well, um, I'm not sharing. Right, okay. I'll make it back on. Right. We'll start again. And this will be finished easily, right? Binomial distribution is used to calculate the probability of a specific number of successes. Yeah, no. Bernoulli's trial. A Bernoulli trial is an experiment that results in one or two outcomes, success or failure. The trials are independent, means the outcome of one trial doesn't affect the other. Example, tossing a coin where head success and tail fail, it doesn't affect number of trials. This refers to the fixed number of trials performed in the experiment. For example, if we flip a coin 5 times, right? Success probability. The probability of success is in trial. Each trial is denoted by P. This probability is constant across all trials. Example, for a fair coin, the probability of head success on each flip is 0.5. Failure probability. The probability failure is denoted by Q, and it is calculated as 1 minus P. Since each trial results in either success or failure, we always have P plus Q is equals 1. For a fair coin, 0.5 for heads, so Q is equals 1 minus 0.5 for tails. Binomial distribution formula. Okay. Mm, Permutation should be C, right? Yep. Yes. Binomial coefficient, which represents the number of way to arrange x successes in n trials. It is calculated as this, right? N factorial by x factorial n minus x factorial. Hmm. Combination. Hmm. Binomial distribution calculates probability of getting exactly x successes in n dependent trials. The formula for a probability mass function is probability mass function of getting exactly x successes. N is the number of trials, x is the number of successes we want to calculate the probability for. P is the probability of success in each trial. Binomial coefficient, which represents the number of ways to arrange x successes in n trials. Probability mass function. The probability mass function defines the probability of a specific number of successes occurring in the binomial distribution. It provides the likelihood of getting exactly x successes out of n trials. The formula for PMF is as follows. This is the formula, and this one, there's no difference. This formula tells us the probability of achieving exactly x successes in n trials, the binomial coefficient This is basically N, P, and Q, right? So, and P gives the expected value, and variance. The variance of a binomial distribution measure how much the number of successes varies from the expected value, and it's this standard deviation. The standard deviation is the square root of the variance, which gives us a measure of how much the number of successes is likely to differ from the expected value on average, right? And it's root under N, P, and Q. Practical example: airline ticket sales. It's already finished. Oh, it's a bit of it. Uh, let's apply the binomial distribution in a real life scenario. Consider an airplane that sells 65 tickets for a flight with a capacity of 60 passengers. The probability that a passenger does not show up for the flight is q is equals to 0.1, means the probability that a passenger shows up is p is equals to 0.9. The airline wants to know the probability that 60 or fewer passenger will show up so that they don't need to reschedule tickets. Define random variable. Here, the random variable x represents the number of passengers who show up. We need to calculate x is less than 60, the probability that 60 or fewer passengers show up. Uh, calculate probability of more than 60 passengers. We first calculate the probability that more than 60 passengers show up, which is x is greater than 61 or equal to 61. That will be probability of x is equals to 61, 62 up to 65. Using our binomial formula, here we calculate the probabilities for these all. We then subtract this from 1 to find x is less than 60, right? So we'll subtract these all, and result after performing the calculation we find x is less than probability of x is less than 60 is 79%. After performing the calculation, we find that the probability of 60 or fewer passengers showing up is approximately 79.09%. This means that there is 79 chance that the airline will not need to rebook any passengers. Yeah. Opposite, 21% chance. Python implementation for binomial distribution. Now let's implement the binomial distribution in Python to find the probability, visualize outcomes, and calculate both PM and CDF. We'll be using NumPy, Matplotlib. It will not work. Yes, yeah, it didn't work. Let me see the code. NP arrange 0 to n plus 1, and binomial PMF, PLD figure, fix size this, and bar title, max level by level. Binom.cdf, scipy stats. You can call binom to find the binomial distribution PM, and binomial distribution of CDF, number of successes, number of with probability, cumulative probability. Okay. Application of binomial distribution. Binomial distribution has numerous applications in real life scenario. Quality control. In manufacturing, the binomial distribution is used to model what to just get out of my head. Binomial distribution is used to model defective item in a batch. For example, a factory produces 100 items and has a 5% defect rate. The distribution can help estimate the probability of finding a certain number of defective items. In retail business, can you and I'm two more. Yeah. Yep. Uniform distribution. Oh shit, I forgot. Market as read. Up. Three left. Yes, we can actually cover this position. Um, who is this concurrent viewer watching me eat? Ha. Mm, mm. I guess this is just a bot because in my stream all with bots. It came to check the copyright. Uninformed distribution in data science, right? Uninformed distribution, also known as rectangular distribution, is a type of continuous probability distribution where all outcomes in a given interval are equally likely. Unlike normal distribution, which have varying probabilities across their range, uniform distribution, uniform, not on gone that sick individual or bots. What do you call uniform? It's called uniform, not uninformed. Uninform, INFORM. It's UNINFORM, uninformed. But this is uniform. Don't pronounce it like uninformed. It should be uniform. Uniform distribution has a constant probability density throughout the interval, which results in a flat distribution. So it gives constant probability. Uh, Key concept: events and interval. 3 views. How are people coming and going, bro? Have you gone mad? Is YouTube Studio gone? How is my video getting 3 views, bro? Bro, yesterday's stream was too short-lived, right? First, because of that streaming software. I didn't know about that bitrate, so so that is why it was like that. Uh, the Yesterday's stream was too short-lived, right? First, because of that streaming software. I didn't know about that bitrate, so damn, the video quality is good. It was like that. Uh, Today's stream was too short-lived, right? Was because what am I saying? That streaming software. I didn't know about that bitrate, so damn, the video quality is good. It was like that. Okay, I'm not talking while using my lips. That is why it's a problem. Done. I've seen enough. I'll not talk. Events and interval. Okay. On uniform distribution. I'm always talking on uniform. It's uniform. Uniform distribution. Yep. Events and interval. Uniform distribution applies to events that are equally likely with a fixed interval AB. This interval can represent time, space, and continuous measurement. The events within the interval are random and independent, but they are all have the same likelihood of occurring. So, who is this? Oh, okay. This was me. The concurrent viewer watching right now is me. I know about it because studio is slow. You not gonna give me heart attack. No one's coming to see this. So, what was I talking about? Yeah, the likelihood of occurring is same. Means that if I want to just stop the stream and go to a movie, okay, the likelihood of you going to a movie and me going to a movie is same. Is what I think. Okay, what this is trying to tell. Okay, let's take an example. If a fair die is rolled each side, 1 to 6 is equally likely to appear, which represents a discrete uniform. Uniform distribution. In contrast, a continuous uniform distribution could model the outcome of a randomly chosen time within 24-hour day where every moment has the same probability. Okay. Probability density function PDF. PDF for a uniform uniform. Why am I saying uniform? It's uniform. PDF for uniform distribution is a constant value across entire interval AB. This is because every point in the interval is equally likely to be chosen. A formula for uniform PDF is 1 by b minus a, where b is greater than x and a is less than x. For any x outside the interval AB, the PDF is 0. Okay, so fx is equals to 0 for x is less than a or x is greater than b. Example for a uniform distribution on the interval 0 to 25, the PDF is 1 by 225 minus 0, 0.04. This means every value between 0 and 25 has the same probability of occurring. So, in interval 0 and 25, the values that are in there, they have equal probability of occurring. Cumulative distribution function, CDF. Uh, Cumulative distribution provides the probability that the random variable is less than or equal to specific value x. For a uniform distribution, the CDF is calculated as cumulative sum of PDF over the range from a to x, and its formula is, wait, what does CDF do? CDF provides the probability that random variable is less than or equal to uh, specific value x. Okay, so fx0, if x is less than a, f x minus a and b minus a, if a is less than x and x is less than b, and if x is greater than b, then it's 1. For a uniform distribution between 0 to 25, the CDF is this, right? It shows that any value, the probability simple for any value x probability. Properties of uniform distribution. Expected value, mean. The expected value of a uniform distribution represents the central tendency of the distribution. It is the average of the lower and upper bounds of the interval, which is calculated as a plus b by 2, right? For a uniform distribution with a is equals to 0 and b is equals to 25, the expected value is 12.5. This means the average value of the random variable x is 12.5. Expected value, mean. Variance of uniform distribution measures the spread of values around the mean, and its formula is b minus a square by 12. Standard deviation is root under variance, so it's b minus a root under 12. Example: uniform distribution in copper wire, Python implementation and application. I'll come back, okay? I'll be right back. Back again. Yeah. Um. Let's apply the uniform distribution to real world scenario. Um. What's the transition being heard through audio output too? Well, well. Hmm. Cadillac. Okay, I don't have anything else. So do that later. Okay, I'm back and we'll finish this three in as much fast way as possible. Okay, as fast as possible. Let's apply the uniform distribution to real world scenario. Suppose the current measured in a piece of copper wire is uniformly distributed over interval of 0 to 25. We can calculate the PDF, mean, variance, standard deviation, and CDF. PDF is 1 by B minus A, right? So 0.04. Expected value is A plus B by 2. Okay, mean that is 12.5, and variance is B minus A square by 12, which is this 52.08, and standard deviation is just square root of these 7 point this square root, right? 7.21, and CDF is basically function of this, right? CDF cumulative distribution function. Random for uniform distribution, CDF is calculated as the cumulative sum of PDF over the range. Okay, but CDF is the probability that random variable is less than or equal to specific value x. Here we implement uniform distribution in Python. We will use NumPy, Matplotlib, and to visualize random samples from a uniform distribution. This ist linspace plot and plotting uniform distribution. Nice. Okay. You may say. Application of uniform distribution. Uniform distribution is used in various real-world scenarios where all outcomes within a specified interval are equally likely. Some common applications include random sampling. In simulations, random numbers are drawn from a uniform distribution to simulate random behavior. Quality control. In manufacturing, they models variation in product measurements when there's no systematic bias. Lottery and gaming. The distribution is used to model random number selection in lottery games and shuffling cards. Random time intervals. If an event is equally likely to occur at any moment within a given time frame, this can model the time of occurrence. Mastering the uniform distribution helps us with a tool for modeling scenarios where each outcome within a specified range is equally likely, and it provides a solid foundation for application in random sampling, quality control, and simulations. The exponential distribution is one of the most commonly used probability distributions in statistics and data science. It is widely used to model the time or space between events in a Poisson process. In simple terms, it describes how long you have to wait before something happens, like a bus arriving or customer calling a help center. Okay, how long we have to wait. For example, if bus arrives at bus stop every 15 minutes on average, the time you wait for next bus can be modeled using an exponential distribution. Probability density function (PDF). The probability density function of the exponential distribution is lambda e power lambda x, where x is greater than 0, right? Where lambda greater than 0 is the rate parameter. How often event occurs, x is the time or distance until the next event. Cumulative distribution function. The cumulative distribution function gives the probability that the event occurs within time. 1 minus e power minus lambda x, where x is greater than or equal to 0, uh, gives mean expected value 1 by lambda and variance 1 by lambda square. And um, mean and standard deviation same. Variance is this. So uh, memoryless property. The exponential distribution is memoryless, which means x is greater than s plus t. Given that x is greater than yes, gives probability of is equal to probability of x is greater than t. This probability tells us that the probability of waiting longer does not depend on how long you have already waited. This is unique to the exponential distribution. What did I just do? Huh? Track, div, create. What did I just do? Block element. Oh, block element. So it was for ads origin block. Okay. Example. Suppose calls come into a customer support center at an average rate of 2 minutes, 2 per minute. Okay. What is the probability that you wait more than 30 seconds for the next call? Solution. Understand the rate lambda. Since 2 calls come in per minute, that means the average rate is 2 lambda 2 calls per minute. Okay, convert time. Find the probability of waiting more than 30 seconds. But since the rate is in minutes, convert 30 to minutes. 0 0.5 minute. Use exponential distribution formula. X is greater than 0 0.5, e power minus lambda x minus 0 0.5 minus 1, 0.367979. Okay, wait. To look at this is correct. What is lambda? Oh, okay. That's probability density function. I said distribution. Sorry, probability density function. Okay. Not now, but before I said probability distribution. I guess probability density function. So the value is there is about 36.79 chance that the next call comes after 30 seconds. Python NumPy as NP, C1 as SNS, Matplotlib as PLT. Before implementation, this knowledge I have some, no need. Set the rate parameter lambda is equals to 1.5, data np random exponential 1 by lambda 1000 is plot, and this is the exponential distribution. The exponential is closely related to Poisson distribution. If events occurs following a Poisson process with rate, then the time between events is exponentially distributed with parameter. Okay. Real world applications, call centers, time between incoming calls, bank queues, time between customer arrivals, web server, time between requests, manufacturing, time within a machine part fails until a machine parts fails, transport, time between buses or trains. Okay, that was first. Uh, This one is very long as its Poisson distribution, and it's super important. Poisson distribution is a discrete probability distribution that models the number of events occurring in a fixed interval of time or space given a constant average rate of occurrence. Unlike the binomial distribution, which is used when the number of trials is fixed, the Poisson distribution is used for events that occur continuously or randomly over time or space. Okay, uh, we'll read that again. Poisson distribution is discrete probability distribution that models the number of events occurring in a fixed interval of time or space given a constant average rate of occurrence. Okay, unlike a binomial distribution, which is used when the number of trials is fixed, the Poisson distribution is used for events that occur continuously or randomly over time or space. This makes it suitable for modeling rare events like accidents, phone calls, or website hits. The distribution is defined by its mean lambda, which represents the expected number of events in the given interval. Key concept of Poisson distribution. Poisson distribution models the occurrence of events within a given time frame or spatial area. These events must occur independently, which means the occurrence of one event doesn't affect the occurrence of other. Additionally, the events should happen at a constant average rate over the interval. The average rate lambda, also known as the rate parameter, which represents the average number of occurrence of an event in the given time period or spatial area. This value remains constant throughout the observed interval. Okay, this is the average rate. Time frame, spatial area, the gene must occur independently. Okay, independently. So we read, and this value remains constant throughout the observed interval. The parameter lambda is central to Poisson distribution and finds the shape of the distribution. Okay. Time or space interval, the interval during which we observe the occurrences of events is important in Poisson distribution. This interval can be defined in terms of time, hours and days, space, square miles, or any other metric where occurrences are spread out randomly and independently. The Poisson distribution formula. The Poisson distribution calculates the probability of observing exactly X event in a fixed interval. The formula for the Poisson probability mass function is e power minus lambda x e power minus lambda x x factorial by x factorial probability of observing exactly X events in interval. Lambda is the average rate of occurrence mean in the interval. X is the number of events for which we are calculating the probability. E is the Euler's number, which is approximately equal to 2.718. This formula allows us to calculate likelihood of a specific number of events occurring in the given time or space interval, assuming that the events occur independently and at a constant rate. Probability mass function. The Poisson probability mass function is used to calculate the probability of exactly X events occurring in a fixed interval. The formula gives us the likelihood of observing X events given the average rate lambda. Let us consider a call center which receives an average 3 call per hour, lambda 3, and we want to know the probability of receiving exactly 4 calls in 1 hour. Okay. We use Poisson PMF formula, and for x is equals 4, e to the power minus 3, 3 to the power 4, 4 factorial 0.168. This means the probability of receiving exactly 4 calls in 1 hour is approximately 16.8%. By calculating different values of x, we can understand the distribution of events for various outcomes. Cumulative distribution function CDF. The cumulative distribution function of Poisson distribution gives the probability of observing at most X events within a fixed interval. It's the sum of probabilities from x0 to xx, which provides the cumulative probability. The CDF is defined as sum from k is equals to 0 to x, p x k, that is fx, and x is less than x. If we want to know the probability of receiving 3 or fewer calls in 1 hour, we would calculate the CDF as 3 or less than 3 addition of these all values. Okay, the sum gives the probability receiving 0 to 3 calls scenarios, exact number of point, expected value of the Poisson distribution. The expected mean of Poisson distribution represents the average number of events we expect to occur in the given time space interval. For Poisson distribution, the expected value is simply AT. For example, if the average number of calls received by a call center is 4 per hour, the expected number of calls in 1 hour is 4. This means we expect to receive 4 calls on average every hour. Variance and standard deviation. The variance of Poisson distribution is equal to lambda, the average rate of events in the interval. The variance tells us how much the actual number of events deviates from the expected number of events. The standard deviation is the square root of variance, which gives us measure of how spread out the number of events is from the expected value. To example, traffic incidents. Let's apply the Poisson distribution in real life scenario. Suppose that traffic accidents occur on a certain road at an average rate of 2 accidents per month. We can use Poisson distribution to calculate the probability of having exactly 3 accidents in a given month. Using the Poisson PMF formula, we get e power minus 2 to the power 3 factorial gives 0.180. Thus, the probability of having exactly 3 accidents in 1 month is 0.180, 18%. Python implementation for Poisson distribution. SciPy library will be used. SciPy the stats, import Poisson and PLT and apply as NP. I'll take a lambda variable as a lambda mean as 3. NP arrange 0 to 10, k from 0 to 10, PMF Poisson.pmf k lambda valuation, and that will give the figure. Again, for the PLT figure size, language, font size, community, plot CDF, plot PMF. So this is PMF Poisson distribution third, 3, and the probability same for CDF cumulative distribution function. This cumulative probability number of events occurring. Probability of exactly 4 events is 0.1680. Relation between Poisson and exponential distributions. Poisson distribution and exponential distribution are closely related probability distribution that describes different aspects of same random process known as Poisson process. In a Poisson process, events occur randomly and independently at a constant average rate over time or space. These two distributions are conceptually different but share a fundamental connection. Poisson distribution models the number of events occurring in a fixed interval of time or space. Exponential distribution models the time between consecutive events in the same process. Okay, models the number of events occurring in a fixed interval of time or space, Poisson distribution, and models the time between consecutive events in the same process. Both distributions are defined by the same rate parameter lambda, which represents the average number of events per unit of time or space. The relationship between Poisson and exponential distributions can be described as follows. Poisson distribution is used to calculate the probability of observing a certain number of events k in a fixed interval, and its formula is this. Like it's exponential distribution describes the weighting time between two consecutive events in a Poisson process. Its formula is lambda e power minus lambda x, where x is greater than or equal to 0. Okay. Lambda is the rate parameter, the average rate of events per unit of time. X is the waiting time between two consecutive events for exponential. Right, application of Poisson distribution. Poisson distribution is used in many real-world scenarios where events occur independently and at a constant average rate. Traffic and accident analysis used to model the number of accidents occurring at an intersection over a fixed period. Telecommunication models the number of calls received by a call center or the number of network requests in a given time period. Medical field in healthcare, it models rare events like the number of new cases of a disease in a given time period, applied to understand the number of customers arriving at a service point, bank, or checkout line within a certain time period. By understanding the Poisson distribution, we get valuable insight into modeling rare events over time or space, which increases our ability to make informed decisions across various industries. Okay, that is that. And we'll go through quiz. What does probability mass function describe? Dun, dun, dun. Probability of discrete random variables, probability of continuous random variables, cumulative probability of all values, the standard deviation of a dataset. Oh, the probability of discrete random variables is the answer. The PMF gives the probability of each possible value of a discrete random variable, like the number of products our customer buys. I was not sure, but it's discrete random variables. Thank God. What does the cumulative distribution function helps us determine? Probability of a single value occurring, the probability of values less than or equal to a given number, average of all values, variance of data set. This should be it, not the single value. Uh, oh, ah, oh yeah, bro gave a heart attack. The CDF tells us the probability that a random variable is less than or equal to a certain value, useful for both discrete and continuous distribution. With probability distribution based for modeling number of customers arriving at a shop per hour. Okay, binomial distribution will give success or failure, right? Poisson distribution will give in interval, right? Normal distribution is not needed. Yeah, modeling count events like customer arrivals happening in fixed period of time. Which distribution is commonly used for modeling wait times between events? Okay, wait times. Wait times is exponential distribution that we yes, exponential distribution models the time between events in a process where events occur continuously and independently, like the time between customer arrivals. Which of the following is the key condition of a binomial distribution? The trial must be dependent. Uh, there must be more than two outcomes. Each trial has the same probability of success. The outcomes must be continuous. Same probability of success, either true or false. Don't know. Oh yeah. Each trial is independent and yes, it's never dependent. That's why I didn't look at it. Continuous also, I didn't look at it. These two were surely not. I was complacent about this. I didn't want to do this. I did this with the same quality assessment every time. Which of the following is the key parameter of the exponential distribution? Exponential distribution. Okay, exponential should be the parameter, right? Hmm. Yup, exponential lambda represents the rate event per unit time. It controls how quick event occurs. Higher lambda means event happen more frequently. It's key parameter. Okay. What type of variable does the Poisson distribution deals with? Position distribution. What type of variable does it? Hmm. Should be continuous, right? I forgot. Shit. Should be continuous, right? Don't know about category. Oh, discrete. Yeah, I forgot. The Poisson distribution deals with discrete variables, meaning it counts the number of events like arrivals, clicks, or messages that happen in a fixed time or space interval. You can only have whole number counts like 2, 1, 0, 1, 2, not decimals or continuous values. Oh, got it. What does Bayes' theorem primarily helps us with? Oh, we read this yesterday. Calculating mean and median. Predicting future values using linear regression. Huh? Huh? Finding correlation between two variables. Being probability of this one. This was one. This is not. This is totally not. This is not. This should be it. Yes. Revise available helping decision. One wrong, 10 right. We've done it, and we passed day 9 using 3 days worth of time. Wow. And we are at day 15 in our session, right? We are 10 days, oh, sorry, 5 days away, 6 days away. This was it, and we'll be looking through 10 tomorrow, okay? It's already my time to go. My time to sign. Oh, it's 2:40. Okay, I'm fine with it. 2:40, it's fine. And 475 is also fine. Done. Good. Okay. This up to we have completed 50%. 15%? Bro, that's a lot. 15% is a lot. We are only starting, right? There's a lot to go through, and finished. I have to do work. I'll get off now, and I'll be researching what to do and completing my project too. But there are a lot of university work I have to do, assignments. Those are never ending. So I'll be late. I will be finishing my project in 1 month, I guess, and then I will start with Moodle. Bye.